Today is, I guess, also our last JQI seminar of the season, and according to tradition, we actually have some of our own give this seminar. Usually, it's two postdocs splitting the slot. So our first speaker is Yuan Chen. He's our outgoing JQI theory postdoctoral fellow. Yuan has an interesting background. He was actually, just a tidbit is he's won medals at both the International Physics and Math Olympiad. I don't know too many people with that credential. And then he did an undergrad at MIT, where he was an experimentalist with Pablo Forero. And then I think he decided that he is done with anything to do with anything, and he went to do a PhD with Anton Kapustin at Caltech, where he studied more topics really many body systems, but from a much more abstract standpoint, and that's part of the same direction that he'll talk about. But between Caltech and here, he spent some time in Google Quantum. So I guess he was then trying to kind of connect back to something that has to do with something. So, all right, Yuan.
Yeah, thank you.
Oh, and Yuan is moving on to a faculty position at Peking University. So he's done well.
Thank you very much for the nice introduction. Yeah, today my topic is called the Pauli stabilizer code of 3C quantum double. So I will explain each term, the meaning of each term later. Sorry, 1 second. Oh, okay.
Yeah, it's up at the top of the screen. So
oh, okay, I see. Yeah, so first I want to thanks for my collaborator. So you can see they are all over in the US and one in Sydney. So they are all postdoc now, and Don is a professor there. Okay, so before I start my talk, I try to give you some background knowledge about what's the recent development in this field. So you can see in the last year and this year, there are some incredible experiment in the Google, and I believe this is in Quantinia. It's some trap ion quantum computer. So they demonstrate they can actually implement some surface code on their either superconducting QB or trap ion device. So for this one, they try to implement key-type surface code. Then they even create some defect in their lattice, and they can actually move this defect on their device, and they can show this defect is actually non-abelian. And the later one, this one, they introduce a technique called feed forward. So it's like during the quantum circuit, they can do some measurement, and based on this measurement outcome, they can further modify the state to prepare the ground state of the toric here. Yeah, so what's the motivation of these two experiments? So besides just to showing the good quality of their platform, so there's a huge area. It's called surface code or quantum error correction code. So we want to design certain protocol like a quantum encoding to try to protect our quantum information. Yeah. So this is the main motivation. So in the real quantum device, we always suffer from some environmental noise and some faulty operation. So we want to find some way to correct those quantum error. And there are two most traditional ways to do it. The first one is the Pauli stabilizer code. So this, like for example, back to early 90s, the Peter Shaw already have the 9 qubit code. So he can use this 9 physical qubit to protect the single logical qubit against any single qubit error. So besides that, there are many famous codes like a 7 qubit code or more general CSS code. So this is one direction, a huge direction we try to design to use the physical qubit to actually protect the logical information. And the other way is called topological quantum code, or more a more famous name is called surface code. It's like on the 2D surface, we try to define certain topological model, like a key-type toric. And more general, this is related to the field theory. So back to the 90s, the Dagua-Witten left the topological quantum field theory, and nowadays we actually try to implement those theory on some at least theoretical quantum computer, and those topological quantum field theory can serve as the error correcting code for our purpose. So in my talk today, I will try to combine these two approaches. So I will find certain topological model, and I will transform them into the Pauli stabilizer formalism. So in this sense, we can have the benefit for these two approaches.
And what are the specific benefits of them individually?
Yes, that's a good question. So I have this slide to tell about pros and cons. But before that, let me just give you more information about the definition of these two approaches. Yeah, so people are more familiar with this Pauli stabilizer code because this model is very simple. Just we write down some Hamiltonian. The Hamiltonian is summing over some product of Pauli matrix. For example, each term can be Pauli x times x or x times y times z, however you want. The only constraint is each term they commute with themselves. So with this condition, solving this Hamiltonian is kind of simple. You just need to find a simultaneous ground state of each stabilizer term. So this is called a Pauli stabilizer code. I think one inventor is Daniel Grossman. I'm not sure if he's here. So he has a famous thesis like focused on this topic. I think it's 1997. Yeah. Then the other way is a little more fancy. It's called topological quantum code. The idea is we try to find some topological system like a key-type toric. So if we put this Hamiltonian on the torus has a 4-4 ground state degeneracy. And we can show that this 4 ground state cannot be distinguished by any local operate. So which means if some local error happens, we cannot go from one state to the other state. So this is a very robust kind of a quantum memory, which is robust against any local perturbation. So this is like we try to encode our information in the ground state level of this specific topological Hamiltonian. Yes.
So the Pauli, so this stabilizer code, you're saying that this was in monosthesis, but this is also related to Thor and Ski?
Yes, because as long as you use the Pauli XYZ, it's just the Pauli stabilizer code. Yeah, it can be more general. You can use like a cleaver or more like a control Z. But for that kind of model, it's more complicated. It's not easy to analyze. Yeah. Okay, let me give you some pros and cons of these two different approaches. Yeah. So first, let's start with the right-hand side, the Pauli stabilizer code. So as I said before, this model is exactly solvable because each term they commute. We just need to find a common ground state for each term. So it's easier for physical implementation because it only involves the Pauli matrix. And this is the most basic operate we can apply on any platform. And also, it's kind of easy to analyze the error correcting property. For example, we can say define the co-distance, which is the shortest operate. We can go from one logical state to the other state, and we can analyze like how many qubit error can be correct in each model. Yeah, but the problem is of this protocol is hard to generalize. So there's a recent development in the LDPC code. They try to scale up this kind of Pauli stabilizer code, but it's super complicated. If you have more logical, if you have more physical qubit and you want to keep the code rate and also want to scale the code distance, it's a very hard mathematical problem. So usually this only works for a small system. If you want to work on, I don't know, 100 qubit or maybe even 1,000 qubit, it's almost impossible to use this method. Okay, on the other hand, the topological quantum code. Yeah, so as I said before, from nature, it protects any local perturbation because it's basically a definition of the topological means. So when we say something topological, this means it's robust against any perturbation. Yeah, and it's a native fault tolerant operate because the logical operate for example, on the torus, we need to apply the very long string operate across the large cycle. So it's very unlikely this kind of operate will happen naturally. So if we scale with the system size, the better the protection. So yeah, so this is the benefit for the topological quantum core. But on the other hand, those quantum core is very complicated. So besides the toric core, we use the Daiguan-Witten topological quantum field theory or Key-type quantum double. So in those model, even write down the operate to move the kind of anyon is very complicated. There's no easy way to find a way to actually analyze the error correcting property for this model. Yeah, so in this talk, I try to combine these two. So I will find certain model and make it into the Pauli stabilizer formulation, and I will have the benefit for both sides. So you can think of this as the step 2. So beyond the toric core, we have already successfully implemented on Google or some IBM's quantum device. We try to search for more exotic topological model which can be implemented physically. Yeah. Yes.
So when people describe topological codes, they frequently say that it protects against all local
Yes.
errors and it scales with the system size. But it seems like you also need the temperature low. And when you mention the temperature, they say, well, it's exponential. So, ignore it.
Yes.
But in practice, you can't always, it can be really hard to get below the gap by a long distance.
Right.
And is that a problem?
Yeah, so when we define the topological phase, it's the zero temperature classification. But in principle, if it's below 40, I think all topological phases are not stable under thermalization. So if you go to high temperature, all these phases destroy. So yes. So in this talk, I kind of ignore that problem, but in reality, especially in the experimental development, it is a crucial point. We need to make sure the temperature is extremely low.
Also, I guess you're talking about topological quantum codes.
Yes. Yeah. Oh, yeah. But yes, so you can kind of so in the real topological material, we care about the real temperature. But if you want to translate into, like, for example, some imaginary topological on some superconducting device, I think those temperatures become kind of a noise rate, for example. Yeah. So the final goal is we still try to compute the so-called threshold. So we need to make sure each physical qubit, the fidelity is above certain threshold, such that this topological code can increase the fidelity or reduce the error rate. Yeah.
But there's the other thing is that has nothing to do with temperature.
Yeah, not physical temperature, but kind of yeah. Yes.
But it's there as an issue.
Oh, sure, but it might be if you get your qubits better, your physical qubits are better, then maybe you could be much below some effective gap. I mean, the physical intuition is also completely different for codes. For sure.
Yeah. Okay, let me just start a very tutorial example. It's called Z4 toric. Some people call it Z4 gate theory. Yeah, so it's very similar to the Key-type toric. It's a Z2 version, and now I just changed the Z2 into Z4. So the only difference in this generalized setting, we have this generalized Pauli matrix. So like the Pauli X and Z, it used to be a 2x2 matrix. But once we introduce this qudit, so qudits mean d-dimensional qubit. For usual qubit, it's only 0 and 1. It's a 2-state system. And now we can replace this by n-state system or like n-level system. And we can define the corresponding Pauli matrix. So we will try to use this generalized Pauli matrix to define the Hamiltonian we want. So this is the most simple example. It's called a Z4 toric. So we can define some vertex term and plaquette term. So we can show that in this specific model, it is a 16-fold degenerate ground state, and they are locally indistinguishable. Yeah. So let's study a little bit about this model. So we can try to see what kind of anyon is contained in this theory. So anyons mean like a local excitation which break like some Hamiltonian term. So first example is the string operator of Pauli Z. So if we apply the Z along certain string, we can see in the middle of string, this Z always commune with this vertex term because 2Z anti-commune with X and X dagger, the phase cancel out. So this string operator only violates some finite term at the endpoint. So we call this local violation of energy. It's called anyon. So it's kind of a quasi-particle in our system. And when we say anyon is non-trivial, which means this excitation cannot be created locally. It must be created by some long string-like operator. So for example, this one, the E anyon here is the single violation of this X term. So if we play around this model, if you just try to apply some local operator here, you cannot obtain a single violation. It must be come in pair. So which means that this single E anyon is non-trivial in this system. Yeah, so we can see there are two types of string operator. One is called anyon E, stands for electric charge, and the other anyon is called N, stands for magnetic flux. So we can see in this Z4 gate theory, we have electric charge and we have magnetic flux, and they are order 4 because I start with the Z4 Pauli. So which means if I apply this operator 4 times, it becomes completely identity. Yeah, so this is the, if we forget about the latest model, so this is the data we write down for this particular quantum code. So we have charge and we have flux, and when they break, they have some non-trivial effect. So it's just like the standard electromagnetism. There's an Aharonov-Bohm effect when we move electric charge around the flux. So in this Z4 gate theory, it pick out the I factor here. So this is the simplest Pauli stabilizer code for a Z4 gate theory.
Why do you call it Pauli stabilizer? Because they're not Pauli.
Oh yes, but so in this talk, our Pauli means this generalized version. So in the future, maybe we have so like superhandling qubit. So far, we only use the 0 and 1 state. So if it's improved, we can use the higher excited state. We will have this kind of qubit degree freedom to have more level to access. So use this kind of qudit, we can represent some model in a simple way.
What's your definition of Pauli?
Just this, just like not 2 by 2 Pauli, but like n by n Pauli matrix here. Yeah. So yeah, due to the time, let me skip some detail. So yeah, so only okay, I want to convey an important message. So in this model, electric charge and magnetic flux, they are boson. When they move around each other, there's no non-trivial phase. But we can consider the charge flux binding. So in this EN particle, it's one electric charge binding with one magnetic flux. For this specific particle, when they move around, they pick out the I phase. So this is kind of not standard because in the usual physics, we only have the fermion. When we exchange the particle, we get a -1. But in this case, when we exchange the particle, we get an I factor. So this is called semion. So it's kind of the half of fermion. So so I want to point out in this specific theory, there's a particle have this semionic statistic. Okay, so since we now understand what's the object data of certain topological, certain Hamiltonian, we can try to classify them. So we can write down many Pauli stabilizer model, and for example, torical, colorical, XZ, XCO. All may look very different, but if we just focus on the underlying data, for example, what's the excitation, what's the anyon behavior, what kind of particle it contains. So actually many example here can be identified. For example, the famous colorical, some people show that it's actually just 2 copies of torical, but the model just look completely different. Yeah, so from now on, let's just try to ignore this microscopic detail, and we just try to capture the universal property, like how many anyon in this model and what's their property. Yeah, So this is the most generic data we can find for each Pauli model. So we can label this anyon by like A1 to AN, and they have some fusion rule, and they have some exchange or braiding statistic. Like for example, this particle, it can be fermion, boson, semion, or more exotic phase. Yeah. So there's a famous mathematical theorem. If you try to use the ZP qudit, which means the dimension is prime dimension, and no matter how you define your Hamiltonian, the final answer is always the torical. So which means if you use the Z2 QB or Z3 or Z5 qudit, whenever you define some Pauli stabilizer model, it must be torical. So it's kind of a boring, like the torical already exhausts all possibility. So in this talk, we find a counterexample for the composite dimension. So if we go from the Z4 qudit, so in the Z4 qudit, we can actually construct some phase which is beyond the Z2 torical. So it actually become a double semion. So this is the main contribution of our paper. We show that if we use the composite dimension qudit, we can construct the topological phase which is beyond the standard torical. Yeah, due to the time limit, I don't have enough time to introduce the detail of this model, but let me just try to skip this technical part and give you some overall physical picture. Yeah, so we find that in the model we construct, it's become a double semion theory. So which means it has 4 kind of excitation. The S and S bar, they are the flux, and B is the charge boson. And the non-trivial property of this semion is when we exchange them, they get the I factor. And sensing this is S bar is anti-semion, you get a minus I. So in this theory, since it contains a semion and the anti-semion, so this theory is usually called a double semion topological order. Yeah, so we have the Z4 Pauli stabilizer code, which realizes this specific anyon theory. And this picture comes from condensation. So we start with some Z4 torical, and we condense boson. So when we say condense, which means the ground state becomes the superposition of all configuration of this specific particle. So in some sense, in this new ground state, this boson is free. So we can get this boson from the vacuum without any energy cost because it already summing over all possible configuration. So after condense certain boson, the new anyon theory become has different property. The first property is some anyon is identified. So for example, in the original theory, this E squared is a non-trivial boson, but since I condense it, so this boson become free. So it's kind of just like a usual vacuum. So these 2 particles become identified. And there's another effect, it's called confinement. If some particle has a non-trivial braiding with this boson, they must be confined. Otherwise, it violates some consistent condition. Yeah. So the idea is kind of simple. We start from the Z4 torical, and we condense certain boson. And this condensation confines certain particle. The confine just means this particle is eliminate, so it's no longer existing in our theory. And the same color of this anyon, they become identified because these 2 anyon, they are differed by this condensation boson. So they become identified. So it's like starting from the Z4 torical, we can play around this anyon by condensing some boson, and we obtain the new theory. So this new theory is exactly the double semion theory I show you. Yeah. So let me try to conclude my talk quickly. So so let me just give you some general result. So this double semion theory is a very specific example of the so-called twisted quantum double. The twisted quantum double is like we start from quantum double like a torical, and we can twist it by some co-cycle data. So it's very similar to the Daiwa-Witten TQFT. So given a gauge theory, we can introduce some mathematical data called three-core cycle. So this three-core cycle can change the behavior of the flux and charge. For example, it changes the fusion rule of this flux, so it changes some property of this twisted quantum double. Like a usual toric has an electron like Z2, E, and N, and when we add the co-cycle, it becomes a double semion. So this kind of data can change the behavior of the original series. And our conclusion is for all possible twisted quantum double, we have the recipe to write down the Pauli stabilizer model for this kind of topological field theory. Yeah. So this has some mathematical theorem by Wheaton. So in one of the Wheaton's paper, he showed that for any non-trivial three-core cycle, you can always enlarge the group to make sure this co-cycle becomes trivial. Yeah, but this is just some hidden mathematical result we use. But just but for physics side, we just need to remember for all possible twisted quantum double, we can always find some staking of toric to reproduce exactly the same braiding and fusion behavior. Yeah. Okay, so I think I end my talk in the in the right hand. So first, in this talk, I show you we define a new generalized Pauli stabilized model for the double semion. So in the future, if our either superconducting QB or other platform allow us to use the Z4 QD, we can implement this protocol on this new platform to actually simulate the behavior of double semion topological order. And yeah, but there's also some future questions. Here I just show you some example, but there are other mathematical questions. For example, given a composite-dimensional qudit like a Z4, ZA, Z16, what's the all possible phase we can write down using a Pauli formalism, Pauli stabilizer formalism? And also, so far we only talk about a non-chiral theory. So is there any possible way to implement a chiral theory on the quantum computing platform? And also, so far we haven't used any time dependence. So we can also introduce a time dependence on this platform. It's called Flaquet code. So there's like a Microsoft people by Hart and Hastings, they use the periodic measurement to implement the Kitaev surface code using only two-body measurement. It's quite incredible. And finally, if we try to achieve universal quantum computation, we need to make sure our system is non-abelian, because abelian cannot produce gate beyond Clifford gate. So we also want to study how do we implement non-abelian TQD onto our quantum computer. Yeah, thank you very much.
One quick question.
Yes.
So let's say I'm an experimentalist. I want to implement these ideas. How expensive is it going to be in terms of experimental resources?
I haven't done any resource estimation, but if we just focus on the model part, we need to have a way to implement a 6-body interaction on the qudit. So yeah, so it's already very costly because the standard toric is 4-body. It's already kind of difficult for most experiment. For most experiment. So people have some design to reduce this 4-body into 3-body and even 2-body in the recent Microsoft like a proposal. So far, to be honest, my 6-body proposal is kind of too difficult for the current stage. But what I hope is in the future, maybe either the experimental side it improve, or series we find another way to reduce this 6-body turn into breaking down into smaller turn, which may be feasible. Yeah.
Have a quick question.
Just how does your combined code stack up? Does it have all the advantages of each one of them?
Oh.
Can you go back and tell us that?
Oh yes. Yeah. Yeah. Because because originally the code provided by either Dagua Wheaton or called Levin Gu, like by Michael Levin and Jensen Gu, they have already defined a model for the double semion. But in the original representation, it's a 12-body and it requires some projector. So it's like this model already exists, but in more complicated formalism. And now I use this Z4QD kind of a trick to kind of reduce their model into a nicer representation. Yeah, but yeah.
Does it have the advantages all six checkmarks?
Yes, yeah. So the left hand side is automatic. Yeah. And the right hand side is because now it's so in the original construction is not stabilizer. It's a commuting projector. So they require some projector to project the ground state. But in my model, it's exactly just stabilizer model. We can write down the ground state exactly. So actually, we just match the double semion behavior into the Z4 torical. So we can just use our knowledge about Z4 torical to analyze the behavior, like error rate, for example. Yeah.
Thank you.
Yeah. Thanks for the questions.
All right, thank you.
Can you hear us in the room?
Yes, yep.
Okay. Mohammed could do the introduction now if he wants.
So sorry, I just wanted to correct that Daniel got his master's degree in Columbia, the country, University of Columbia. And then he did his PhD in Lecce, Italy, studying exciton polariton. Then he's one of those brave souls who decided to work in a lab and then moved during COVID. So he joined my lab and he's been doing very interesting, fantastic works. This is one of them. So I hope you enjoy his talk.
Thank you very much, Mohammed, and thank you very much for the introduction. So yeah, my name is Daniel Suarez. I'm a postdoctoral researcher, as Mohammed said already, in his group. And thank you very much for the opportunity of sharing with you today some of our recent results. In particular, I'd like to share with you today the results we recently obtained in heterostructures made of 2D materials. Today, I'd like to show how one can harness the properties of a heterobilayer of tungsten disulfide and tungsten diselenide to host a Fermi-Bose mixture with very good properties in terms of real-time controllability of the density of fermionic and bosonic particles, and how one can achieve Mott insulating states in such material. So the physics of this system can be well reproduced by the Hubbard model. So this is the main interest because this model is it takes many good insights into the physics of many body systems. It only has two terms, but as simple as it is, it reproduces a huge amount of effects. So we have two terms, one term that goes as T with the parameter T that accounts for the capability of the particles of hopping in a periodic potential, and a term U that accounts for particle-particle short-range interactions. So in summary, this model can reproduce an array of particles in a periodic potential with short-range interaction. And it then raised the interest of the community because it can describe very interestingly the superfluid to Mott insulated transition in its bosonic version. So the way to achieve such states is not trivial because one needs to treat the system or manipulate the system in such a way that the hopping term becomes comparable or lower than the interaction. So basically everything is about enhancing the interactions in the system. So one way to do it is by confining the Wannier orbitals of the particles in the system, so making them more confined. And this was achieved some years ago, well, several years ago, in atomic arrays. But more recently, it was very celebrated, the result in which this was achieved in a transition metal digital cogenide system, in particular in a bilayer. The way in which this was manipulated in that material is by changing the properties of the crystalline structure by stacking together similar materials in terms of crystalline structure, but with a slight mismatch. So this is gonna be reflected in a moire pattern that then is gonna change the properties of the confinement of the particles. So we can pass from a lattice constant of units of angstroms, 3 angstroms for tungsten diselenide, for example, and when stacking together a monolayer of tungsten diselenide, one can achieve this 4% of mismatch will create a much larger pattern in which the distance between the unit cells is not anymore in the angstroms, but in the nanometers. So we can pass from 0.3 nanometers to 8 nanometers. And then this was harnessed to demonstrate the mentioned effect. Now, the achievement of mode insulating states has been proved both electrically and optically. Our interests rely more on the optical part. So I'm gonna go over it a little bit, how to demonstrate formation of mode insulating states in these materials through optical measurements. We then start by the structure, the band structure of our 2 materials, the tungsten diselenide and the tungsten disulfide. It is a so-called type 2 band alignment, and we can dope the system via a gate voltage. So basically, we can tune the number of electrons or holes in the system. By doing this, and while monitoring the optical properties of one of the monolayers, this can be achieved. For example, as we tune the density of electrons in the tungsten disulfide, while monitoring the optical properties of the intralayer exciton of the tungsten diselenide, one can observe that there are some specific values of the gate voltage for which there is a slight modulation of the energy of the exciton. This is then associated by to the formation of mode insulating states. And indeed, if one make the math using a capacitor model and verifies how many electrons per unit lattice size are there, we can obtain that at this particular point, at this particular gate voltage, there is indeed 1 electron per unit cell. So this is one of the optical ways to prove the physics. Another way to do it is by using the interlayer exciton, which is an exciton formed when an electron in the tungsten disulfide binds with a hole in the tungsten diselenide. So it is indirect in the sense that each particle is in one of the monolayers. And in this case, the mode insulating state reflects as a band gap, as a gap in energy in the photoluminescence emission of the material. So these two possibilities were demonstrated, and we are going to use in particular the second one, photoluminescence spectrum, and our interest relies in the electronic doping of the material. Yes, please.
Experimentally, how to tune the inter and intra dissipation?
So this first measurement is an absorption measurement. So it tells you about the available states in the system. So you basically shine with white light and you see the light that is being absorbed. And in this case, it is the emission, so the occupied states in the system. It is a photoluminescence experiment. So you excite out of resonance, and then depending on the particles that you have in your system, you will collect the optical emission from there. Now, we can also have a very good degree of control, as I mentioned in the first slide, in terms of the Bose-Fermi mixture on the material. How? Well, as I mentioned, the top gate and the bottom gate will control the density of electrons in our system, so the fermionic density in the system. But at the same time, so as I mentioned, at the same time, we can have an optical pump in the material. So not only we can have it, but we need it in order to have any signal that we can detect. So the way to do it is we excite out of resonance optically. Then this creates a plasma of electrons and holes. They will decay non-radiatively, bind together, and form interlayer exciton. And we can then achieve, depending on the intensity of the pump, situations in which we populate only with excitons the material. but because of their nature, we are then controlling the bosonic population in the system. So we can have then two independent parameters on the fermionic and bosonic populations, and that's the physics we are exploring here. Then the interplay between these two parameters can give us interesting situations. For example, we can start from an empty lattice with very few excitons, just to have some optical signal that we can detect. But if we increase the doping level, so we dope with electrons our system, we can achieve the Mott insulator state. And this exciton is not going to be anymore in an empty lattice, but it's going to be in a completely occupied lattice of electrons. Then the properties, the optical properties of this exciton are going to be modified because it has to overcome the repulsion in the inside repulsion, and the energy of the exciton is going to be modified. And we can then keep, for example, reduce slightly the number of electrons in the material, but increase the number of bosons by increasing the optical intensity. And we can have then a mixture between bosons and fermions in our material. So we can effectively achieve Bose-Fermi Mott insulating states in this material. The comprehensive understanding of this material, of these situations, gives us a very interesting phase diagram in which we have an edge with incompressible states and then a compressible bulk in the middle. Now, I'm gonna then show our measurements and how I'm gonna try to convince you that we are actually achieving Mott insulating states in the material with optical means. So the first observation that is an indication of this is an energy gap in the photoluminescence. So that's already I already mentioned how that can demonstrate the formation of Mott insulating states. We can then start with a very low intensity, pump intensity in the material, so very few bosons just to probe the material, and we can tune the gate voltage by increasing the number of fermions in the system. We can start then at this edge where there are no electrons and no excitons in the material. So this is, let's say, the trivial case. But now we can go all the way up to a voltage at which we observe the dimension gap. So in this case, we are in a Mott insulating state of fermions, and we are measuring excitons in presence of that state. But now we can also generate these kind of states optically, so populating with bosons our system. How do we achieve this? Well, we can increase the pump power, and then we monitor the total PL power of the material, which we assume is proportional to the number of excitons in the device. And notice how, as we increase the total PL power, the gap energy again takes place. So what is the situation? We start again from an empty lattice, and as we increase the optical pump, we achieve an excitonic population in the material that strongly interact, achieving the mentioned gap.
Sorry, what gap are you talking about?
So in this case, it is
So that one I get it.
yes, and in this case, I don't know if maybe it's not super evident, but in here, do you see that there is also emission from this state? It's gonna be more evident in the next slides. So this is please I want you to focus on this video, because we're gonna show how, when modulating or changing the density of fermions, of electrons in the system, we can modify the properties of the material for different pumping powers. So as we modify the bosonic population, we're gonna see how the dependence on the fermionic population changes. So notice how the gap moves to lower voltages. That means that every time we need less and less fermions to achieve Mott insulating states. So we are basically populating our device with bosons and with fermions, and they are strongly interacting, giving rise to the mentioned gap. By the way, this is the reference where these results can be found. May you be very interested. And so that was the first observation, the existence of the gap. The second observation is the saturation of the PL intensity. So far we can then, I have mentioned how we want the gap, the existence of the gap, benchmarks the formation of multi-insulating states. For different pumping intensities, we have then different voltages at which these states take place. And we can then reach a situation in which we have a Fermi-Bose mixture in the material. But now I didn't say anything about the intensity of this photoluminescence, which is indeed a very important quantity because it can give additional information. Now, to account for this, we use a computer routine to extract information about the peaks that come from X1 and X2, which is the singly occupied sites or doubly occupied sites. So when an exciton is in a singly occupied site, it emits a photon with X1 energy, and when it is in a doubly occupied site, regardless of it is a boson exciton electron or two excitons, the energy of that exciton is going to be anyway X2. So by monitoring the relative intensities, we can have additional insights into the problem, because when we change the gate voltage, we can notice how the photoluminescence from X1 actually quenches. The way to understand this is we have an initial number of excitons in our material that we're going to keep constant over the full range of gate voltages. And then as we start modulating or changing the population of fermions, then some of the lattice sites are going to be occupied by electrons. And in the limiting case, then there are no any more sites in empty sites for excitons to form. So now the next exciton needs to be formed in an already occupied site. And then this is the effect in the emission of X1. Then we can have this for different intensities, and then every time this takes place at lower and lower gate voltages. So the electronic filling factor sets in the maximum number of excitons in empty sites that we can collect photoluminescence from. We can also do the opposite, fixing the number of electrons in our material and then tuning the number of excitons. So in this case, for example, we start again from an empty site, and we can achieve the formation of doubly occupied sites optically. And as one tunes the electronic density, so for example, if one sets the filling factor to 0.7, which means that 70% of the Moire sites are full with one electron, and 30% of them are free, then this is the situation. And if one analyzes the behavior of the photoluminescence intensity, one will notice that it actually saturates as one increases the number of excitons in the material. So we are saturating the system with bosons, and then there is a threshold after which all the system is effectively populated with bosons. And then the third evidence of formation of multi-insulating states comes from the diffusion of the excitons. So the way we do this experiment is we pump our system non-resonantly in a particular with a very small, almost diffracted limited beam. This will then create a population of excitons that, due to their nature, is going to propagate. And after some time, depending on their properties, they will recombine. And this recombination, we will measure it with spatial resolution. So we can know what kind of exciton recombined from where. This is the kind of figures we can get. We have then the diffusion in this, the diffusion distance in this axis, and the energy in the horizontal axis. So notice how one can pump at this at zero, at y equals 0, and then the population of excitons from singly occupied sites is gonna diffuse in the material, and one can observe such diffusion. Now, yes, please. So in this case, for example, we are very close to an edge. The material is very homogeneous. So there are, yeah, this is not ideal material by far. So they diffuse in this case downward. But notice that what happens when we increase the intensity of the optical pump. You can see the diffusion suppressed. So all we did from here to here was increasing the intensity of the optical pump. And by doing that, we suppressed the diffusion of the excitons, of the X1 excitons. So this then can be understood as if an exciton is in a free lattice, it can diffuse freely. But now, as we start populating that lattice with other excitons, what happens is that because of the U-terms or the short-range interaction, they will lock each other in a mode-insulating state, and then the diffusion is going to be suppressed. And that's precisely what we are observing here. So if we reconstruct the full picture by modulating the density of electrons in our system, so changing the filling factor, one can observe that as we increase the intensity of the pump, the system behaves as expected for a low population of electrons. It behaves as expected from a weakly interacting gas of bosons. One increases the pumping power, so we have more and more bosons, and then the diffusion distance increases. So this is expected from a weakly interacting gas of bosons. But then this limit is interesting because there is a threshold after which this trend inverts. So now higher pumping power leads to lower diffusion in the material. And then this is benchmarking the formation of mode insulating states. So let me finish by summarizing the results. We then demonstrated mode insulating states in a Bose-Fermi mixture of particles in 2D, in heterostructures of 2D materials, benchmarked by 3 observations. The first one is the energy gap in the photoluminescence spectrum, the saturation of the PL from singly occupied sites, and the suppression of the diffusion of excitons in this material. And also some nice potential of this material, of these devices, is that one can control in real time the population of bosons and of fermions completely independently. This is the full reference to this work. And then the outlook is, well, many interesting possibilities come because one can then study the dynamics of these kind of systems, or the steady state, because one can pump CW with a CW laser or with a pulse laser, and then one can have information of the dynamics of this material, of what happens in the dissipative-driven steady state. Also, the optical investigation of a spin charge or fractional states upon the improvement of the experiment of the fabrication techniques that will lead to more ordered samples. And finally, how we are interested in studying how the correlations between the particles lead to photon correlations in the emitted light. So the G2 measurements in these kind of materials. And let me finish by acknowledging my group, of course, Mohammed in the leading all the projects, and then for this particular work, Benigao, who made all the samples and led this project together with Supatrik Sarkar. And from the theory side, Sunsheng Wang, who collaborated very strongly with us in the interpretation of the results, and our collaborators here in the University of Maryland and overseas, and of course, the funding agencies that make this possible. So thank you very much for your attention.
Very nice work.
Thank you very much.
Spectrum where you looked at the response as a function of power.
Yes.
Is there hysteresis in that at all?
We didn't notice any hysteresis, but there is a reason. There is a reason for that, because we are this spectra that I showed. For example, say this one, right? This is pulse regime. So we actually don't expect any hysteresis because we send a number of pulses and then we interrupt. So the system goes to the ground state again. Yeah. So we didn't do the back and forth in CW.
Couple questions about the setup. And for instance, you're trying to get
you're trying to stay in the modern splitting regime where U over T is large. But you go to this greatly expanded Moiré lattice, which I would tend to think would reduce U over T by making the particles on average much further apart within each planar orbital. So I was kind of curious about what was going on there, and if it was that you really needed access to the bilayer exciton, and sort of why was that? Why not use an exciton within a single layer for this?
Okay, so the first comment is U is on-site interaction. So that is regardless of your lattice is bigger or smaller, U is the same, right? So what we are actually changing because it only accounts for two particles in the same unit cell.
But if that site is larger.
Yeah, if that site is large, no, because in the but the particles in the monolayer TMD, they are gonna be very delocalized. So this localization is not gonna take place. So this Moiré lattice is actually a confining potential for the particles that lead to that. So we are magnifying U by confining the particles more, but we are also suppressing T by making the lattice more separate. So the unit cell is going to be bigger, and then the particles are going to have harder time tunneling over the lattice. So that's the key point, I think. I don't know if that's okay.
Yes, right. If I want to build out a theory for the system, so the one immediate question I have is what's the temperature? Because when this is a driven system, right? So it's not clear to me if I can just I guess my question is that if I want to build your system as a post-Fermi model, then how should I think about the effective temperature?
Yeah, that's a very interesting question because indeed, just at zero temperature, the physics is very complicated. So increasing the temperature, I wouldn't be sure, and I think that's an open question that no one really knows. I mean, just at zero temperature, the Bose-Howard model is still a matter of investigation. So how the temperature affects the system is.
May I add a comment?
Yeah. Yes, please, Mohammed.
So, so on the electronic side, if the system is not driven, the situation of temperature is understood, right? It's just the base temperature that we can measure, and hopefully that's exactly the temperature of the sample. On the driven side, I think that's the question, and that's actually still an open question. So this is a driven dissipative system. We are pumping photons. They strongly interact with each other and they leave the system. And what we see is that they strongly interact, they interact stronger than they decay. So otherwise we would not have been able to see this jump in the PL or in the diffusion. But can we assign like a chemical potential or a specific temperature for these driven dissipative systems? We don't know. And that's kind of an open question, how you can understand this phase diagram in physically relevant parameters when you have this driven dissipation, drive and dissipation at the same time. I hope that clarifies at least what the level of our understanding so far.
Thank you, Mohammed.
So you had a question?
Yeah. So I want to come back to the whole idea of the bilayer and the Moiré pattern. When you show us these cartoons of this is fine.
Okay.
Yeah, I just looking at a cartoon, right? And the upper left there. Is each site that the cartoon shows a Moiré site or a single layer site?
A Moiré site.
Okay.
Yeah. So this is the bilayer.
Okay, great. Now, in trying to understand what you've actually done, I mean, it's kind of amazing. You have fermions and bosons, and you can independently control how much of each, and that allows you to move the mod insulator transition all around. That's beautiful.
Thank you.
When I look at that, I wonder if I had independent control of the fermions in each layer. Not that I have any idea how you would do that, but if I had independent control of, say, holes in the bottom layer and electrons in the top layer, would it be the same thing? Because that looks like what you're doing.
Yeah, so in that regard, there is a restraint on a constraint in where we put the excitons, which comes from the band alignment. So we can dope the material, but we can only put electrons initially, for example, in this case, in here. You see that the conduction band of the tungsten disulfide is lower in energy than the tungsten selenide. So I cannot choose what band to dope. At least not in this device.
Yeah.
So that's one constraint, and then that is also the reason why the interlayer exciton forms exactly like this. So we cannot form the opposite interlayer exciton, but it has to be like this because the conduction band, how they align with each other.
Okay, so what are you saying then that if I had this magical system where I could independently control the carriers in each layer, I could do this, but I could do more?
Yes, and I think that there are works. For example, I remember from Atashimamoglu, they kind of isolate one layer from each other, but with a very thin layer of an insulating material, HBN. And in this case, they can independently tune the density on each monolayer, and yet very fun physics come from there.
And so then they can create something that looks like this. In other words, something that looks like bosons and fermions because of the interlayer.
Yes, and indeed, for example, recently there is a paper also in Nature where they demonstrate the formation of exciton Bose condensation by doing that, adding electrons to one layer and holes to the other one. They bind together and then they condensate, but with infinite lifetime because they don't tunnel, they don't recombine.
Any other questions? Well, if not, let's thank both speakers.
Thank you very much.